Let's take a closer look at these enhancements, starting with the new data memory map. Users familiar with the mid-range PIC microcontroller architecture may remember that the PIC microcontroller data memory is organized into 4 banks of registers. On the new enhanced architecture, data memory is now expanded to 32 banks, with bank 31 offering some special functions. The first 12 bytes of every bank are now identical and will hold the core or CPU-specific registers. To access any register in the data memory map when programming an assembly, the user needs to ensure that the bank holding the target register is selected in firmware before it can be accessed. This is called banking. With the core registers common across all banks, they can be easily accessed from any bank, minimizing the need for banking, thereby reducing code overhead. So what are these registers? Here are the common core registers on the new enhanced architecture. I have highlighted some new additions. Let's take a look. As I mentioned, there are now 2 16-bit file select registers, or FSRs, used for computing memory addresses at runtime, allowing data modification using what is called indirect addressing. Since data memory is an 8-bit register space, each 16-bit FSR will consist of 2 8-bit registers, FSR low and FSR high. Along with the new FSR registers are the associated 8-bit indirect file registers, INDF0 and INDF1. A new bank select register has been added. Writing to this 5-bit register selects any of the 32 memory banks in a single instruction clock cycle, a reduction of 1 clock cycle from the traditional method used on the existing architecture. This register also comes with a new associated instruction that we will discuss later. You may have noticed that the working register is now included in the data memory map. The new enhanced architecture now makes the working register completely addressable. Traditionally, on the existing architecture, to save the context of such registers as the working, status, and PCL register, the user simply copied the code from the Microchip supplied template into the firmware. On any interrupt, this software routine saved the required core registers, then performed the interrupt service routine. The enhanced mid-range architecture now does this context save in hardware, eliminating the need of the software overhead. On any interrupt, the contents of these registers are automatically saved. The retfi, or return from interrupt enable instruction, automatically restores the context in addition to setting the global interrupt enable bit, GIE. As I mentioned earlier, with an extended memory map, there is now a lot more room for peripheral specific function registers, or SFRs. In the enhanced architecture, 20 SFRs immediately follow the 12 common core registers in each bank, up to bank 30. The next 80 bytes of bank 0 to 30 hold the general purpose RAM. These registers hold such data as variables created and used by your firmware. This expansion further enhances the data memory space for such high-level languages as C that require room in data memory for variables created in the background. When we look at indirect addressing enhancements, we'll see that these registers are shadowed or mirrored as a linear GPR region in the file select register map. Another nice addition, the last 16 address spaces in general purpose RAM is common across all banks. Similar to the 12 common core special function registers, any data written from address 112 to 127 is accessible from all 32 banks, further minimizing the need for banking when targeting these registers. Bank 31 of the extended data memory space offers some special features for advanced firmware applications. First, the user now has full access to the 16 levels of the hardware stack for read-write operations via some new stack registers. These enhancements allow such neat tricks as changing the return location during an interrupt or creating substacks for different operations. Another feature of Bank 31 relates to the automatic hardware context save. A section of Bank 31 registers contain a backup copy of the saved context and are the source used when the context is restored on a return from interrupt. Therefore, if these registers need to be adjusted during any interrupt, they can be accessed here.